Hello everyone and welcome to our channel, Inspecting Cybersecurity. In this video, we will explore how the Domain Name System, or DNS, enables users to access websites using simple domain names instead of complex IP addresses. We will cover DNS architecture, query resolution, record types, caching mechanisms, security considerations, and modern DNS protection technologies. By the end of this presentation, you will have a solid understanding of how DNS operates behind the scenes and why it is considered one of the most critical services on the Internet. DNS is often called the phonebook of the Internet. Humans prefer to remember names such as google.com or youtube.com, while computers communicate using numerical IP addresses such as 142.250.x.x. The primary purpose of DNS is to translate a human-friendly domain name into an IP address that computers can understand. Without DNS, users would need to memorize IP addresses for every website they want to visit. DNS provides the abstraction layer that makes Internet navigation simple and user-friendly. When a user enters a website name in a browser, a remarkable process begins. The browser sends a DNS query requesting the IP address associated with the domain name. DNS infrastructure processes the request and returns the correct address. The browser then uses that IP address to establish communication with the target server. This translation process happens in milliseconds and is repeated billions of times every day across the Internet. Let's examine the structure of a fully qualified domain name, or FQDN. Using the example www.example.com, we can identify several components. The root domain is represented implicitly by a dot at the end. Below the root is the top-level domain, or TLD, such as .com. Next comes the second-level domain, example, which identifies the organization or owner. Finally, the host name, such as www, identifies a specific service or system. Understanding this hierarchy is important because DNS resolution follows this structure from right to left. DNS is not a single server but a globally distributed hierarchical system. At the top are the root DNS servers. Below them are the TLD servers responsible for extensions such as .com, .org, and .net. Further down are authoritative name servers, which contain the official DNS records for a domain. DNS resolvers communicate with these layers to obtain information on behalf of clients. This distributed design allows DNS to scale globally while maintaining reliability and performance. This slide illustrates the journey of a DNS lookup. The process begins when a user enters a domain name into a browser. The operating system forwards the query to a DNS resolver, which first checks its cache. If the answer is unavailable, the resolver contacts the root server, then the appropriate TLD server, and finally the authoritative name server. Once the authoritative server returns the requested record, the resolver passes the result back to the client, and the website connection can proceed. There are two major DNS query methods, iterative and recursive resolution. In an iterative query, each DNS server provides the best information it has and directs the resolver to the next server that may know the answer. In a recursive query, the resolver performs the entire lookup on behalf of the client and returns the final answer. Most end-user devices send recursive queries to local DNS resolvers, while the resolver performs iterative communication with the DNS hierarchy. DNS performance relies heavily on caching. Whenever a DNS response is received, the resolver stores that information temporarily in cache. The duration for which a record remains cached is controlled by the time-to-live value, commonly known as TTL. Caching significantly reduces DNS traffic, improves response times, and lowers the load on authoritative servers. Negative responses can also be cached, preventing repeated lookups for non-existent domains. Registering a domain involves several entities. ICANN oversees Internet naming authorities and coordinates the DNS ecosystem. Registries manage specific top-level domains such as .com. Registrars act as intermediaries that sell domain registrations to customers. Many organizations also use resellers and privacy services to simplify management and protect ownership information. Together, these entities enable businesses and individuals to obtain and manage domain names. DNS stores information in resource records, commonly referred to as DNS records. The record maps a host name to an IPv4 address. AA records perform the same function for IPv6. CNAME records create aliases for other host names. MX records identify mail servers. TXT records store informational text, often used for email security technologies such as SPF, DKIM, and DMARC. SRV records define service locations, while PTR records provide reverse DNS lookups. DNS was originally designed without strong security controls. As a result, attackers can attempt cache poisoning attacks by sending forged responses to a resolver. If successful, users may be redirected to malicious websites while believing they are visiting legitimate destinations. This technique can be used for credential theft, malware delivery, or traffic interception. Modern security controls such as DNSSEC help reduce these risks. DNS infrastructure is also vulnerable to denial-of-service attacks. Attackers may flood DNS servers with excessive requests, overwhelming resources and preventing legitimate users from receiving responses. Attack techniques include DNS query floods, NX domain attacks, and other amplification-based methods. Organizations must implement rate limiting, redundancy, traffic filtering, and monitoring to maintain service availability during such events. To strengthen DNS security, several modern technologies have been developed. DNSSEC provides cryptographic validation of DNS responses, helping prevent tampering and spoofing. DNS over HTTPS, or DO, encrypts DNS traffic using HTTPS on port 443. DNS over TLS, or DOT, encrypts DNS communications using TLS, commonly on port 853. Organizations should also maintain secure endpoint configurations, patch DNS infrastructure, and continuously monitor DNS activity for suspicious behavior. This final technical slide brings together the complete DNS ecosystem. It starts with domain registration and authoritative zone management. Queries then flow through caches, resolvers, root servers, TLD servers, and authoritative servers to obtain the requested information. Security technologies such as DNSSEC, DO, and DOT provide protection throughout the process. Together, these components create a resilient, scalable, and secure naming system that supports the modern Internet. Thank you for your time and attention. We have explored how DNS translates domain names, how the hierarchical infrastructure operates, how records are resolved and cached, and what security mechanisms help protect the DNS ecosystem today. I hope this session has provided a strong foundation for understanding one of the Internet's most important services. Thank you, and I would be happy to answer any questions.